Okay, recording. Okay. Okay, so this system is something you may have seen maybe on the midterm or studying for the midterm or something like that. It's called an Atwood machine. So basically the whole system is really what you see is what you get. There's one mass that's heavier than the other mass. It's attached to a pulley with some string that kind of connects the two of them. And because one mass is heavier than the other mass, there's an imbalance of forces. And so really quickly, I just want to write out these forces because you know this background, it's not meant to be super explicit and good in like a good teaching or pedagogic way. It's just kind of meant to give you the equation right here that you need for the whole lab. So basically what I'm going to do in you know, the first 10 minutes or so is just tell you how you get 5, just basically just from this picture. Is really how you get it. These are a little confused. This one, we'll use this one in a second. Okay, so firstly, let's draw 2 pictures. The first picture is thinking about things just from what we see occurring. And I'm going to call this the net picture, kind of like maybe in class you've seen like F net or A net. It's like the total. It's kind of the total thing that's happening is if M2 is bigger than M1, then A2 is going to go down and M1 is going to go up. And so I have an acceleration upwards and an acceleration downwards. And I'm not talking about gravity at all yet. I'm just thinking about this is what I see happening. This is going down, this is going up. And so I have force 1 and the force 2. One of the things that I take into account immediately is that both of these things are connected on a string. And so if one of them goes down with acceleration A2, the other one is going to go up with acceleration A2. So the thing that I do automatically when I write this force equation, I'm just doing F equals ma for each of the masses and each of their accelerations. However, because they're connected by a string, both of the accelerations are equal. And the next part is to kind of break things down into what's going on physics-wise underneath, which is what I'm going to call like the component picture. So not what I'm seeing, but what is causing these net accelerations. And here's where the direction of the arrows and as well as the size of the arrows actually matters. So because M2 is bigger than M1, these arrows should be a little bit bigger. This one should be down to this line or so, and that one should be where it is. M2, I don't know why I said G2. I just kind of wanted to draw a parallel between these two things. G is the same for both of these things. So you can just cross out that G1, it becomes G. And so I have that the bigger mass has a bigger force downwards than the smaller mass. So this arrow is supposed to be bigger than that one. Because the net acceleration is downwards, I know that that arrow, the tension of the string pulling up on my mass 2, must necessarily be a smaller vector than this one, because I know what I see is that 2 is going downwards. So this vector here, the force due to gravity, is bigger than the tension force. The opposite is true on this case, because I know that this one's going up, so the tension for the first mass must be bigger than the gravity force on the first mass. And now I'm just going to make some kind of just pictorial. Like I'm just going to look at the pictures and think about the absolute magnitude of the forces. And I know that because this one is going upwards, I know that this is a bigger quantity than this. And so that's why I'm arranging it like T minus M1G. And on this one, I know that this quantity is bigger than this. So I'm just doing this to make them both positive numbers because I don't actually care about the direction of the forces. I can see them with my eyes and I know which way they're going. What we're doing is we're gonna find G at the end of the day in the lab. That's almost all the first half of the semester is just verifying that the acceleration due to gravity is 9.8 meters per second. And so that's why I write this one first and this one second. And then in this case, this one first and this one second, because that's bigger than this and that is bigger than this. And now what I do is I have 2 equations for the same quantity. And so I equate them. I say, let's say that this thing is equal to this thing, and this thing is equal to this thing. And then I have two equations. The first thing I notice is that I'm going to measure A from log or pro. The M's, those are known quantities. So these are kind of like dependent quantities. We'll get to it in a second when we get to this equation down here. But A is a dependent quantity, and I'm going to measure with log or pro. G is what I want to find. So as we can already see from this equation over here, G is going to be our slope. That's the thing you want to find is always you put it in your slope. And you plot the independent on the x-axis and the dependent on the y-axis. But one thing that we don't take into account for this experiment is the tension in the wire. And so what we're going to do is solve one of the equations for T. Right here, I'm just bringing M1G to the left-hand side. So it's T on the right-hand side. I flipped it, so now it's on the left-hand side. And then once I have this equation for T, I'm going to plug it into the second equation. So now I have M2A2, it's up here. I don't know why the arrow's down here. It should be right here. M2A2 equals M2G minus, and then parentheses around this whole thing, M1A2, M1G. And then I distribute the minus sign so that it's minus, minus. And then I bring the things to the left-hand side that have to do with A. So you see this is an M2A2 that stays. This M1A2 I bring to the left-hand side. And I do the same thing with G. I keep these two on the left-hand or the right-hand side. Because then I factor out my A, because both of these two things have an A in them, and both of these two things have a G in them. I have this quantity G, this quantity A, and then I solve for A. A equals this quantity, the subtraction, the difference between the two masses. So like if it's a 50 gram and a 30 gram, that difference would be 20. And then over the sum of those masses. So 50 and 30 would be 20 over 80. That's like 1/4. And then I have my G right here. And so if we compare this equation again, this is something we do, every lab for the first semester, for the first half of the semester, we take this quantity. Notice that that is something that we input into. So for instance, if we look at our data table, that is always something that's yellow. Like it's usually the first thing that we put in. These are independent quantities because nothing is going to change the fact that the weights we're using is 50 and 30. But what does change is the acceleration due to those things. So depending on what the mass is, the acceleration is different. And so this is our dependent quantity. This is our independent quantity. And so we make this y equals, it's written a little backwards, y equals xm plus b. So we compare this to our y equals mx plus b that we did, every single lab. And so what we end up doing at the very end of the day is we put this on the x-axis because it is our independent variable. We put this on the y-axis, which is just an average of the accelerations that you use. You can disregard this. I don't know why I did that. That's not on your data sheet, but for some reason I thought you needed it yesterday in lab, and someone pointed out to me that I was reading things wrong. You actually do not need the uncertainty of every quantity to get the uncertainty of the average. I was reading equation 3 in the error manual incorrectly. I'm so used to a mouse that I don't know how to highlight with a trackpad. Anyway, ignore H and J. You guys don't have those. I just put them in for some stupid reason. And so this average of these three quantities is your y-axis. And then what you do is you plot this using your plotting tool on the y, plot this on the x, and then the slope is already G, because if we head over to our equation, there's no like manipulations like the last few labs where we had to divide by 2 or square root with the h and the time down and all that. Whatever the slope we get applying these two things is already G. So it's a pretty quick one once you have the graph. One thing I just wanted to mention before, one thing that you need the plotting tool for is the uncertainties. So if you notice here, we're just going to assume, even though as you can see, I was pedantic and I weighed all my masses, and you can see they're not exactly what they say they're supposed to be. that was supposed to be 100 and it's not. But whatever, we're just going to assume that they are what they say they are. And so this quantity here doesn't have an uncertainty quantity. And so when you put in your plotting tool, the x-axis won't have an uncertainty, but the y-axis will. And because it does, the plotting tool will give you an uncertainty in your slope. And so that's what you get for this. One thing I wanted to point out though, if you want to, like for instance, if you're running late one day, or if you're like if you're pretty behind on the lab, for like the equipment isn't working, one thing you can do quickly instead of copying and pasting things into the plotting tool is to use this function in Excel, which is just called the slope. So what I did here was, once I do this, you'll see what it says. So equals slope, equals slope. It doesn't come up anyway. Usually it'll come up as like, hold on, equals slope. It doesn't come up anyway. What I was thinking, when you use the Excel, like an actual, like the Excel application instead of Google Forms, it prompts you to tell you like what belongs in this thing. But anyway, what belongs in it is first the y values. You can click and drag your y values, put a comma, and click and drag your x values and put a comma, not a comma, a parenthesis, and then close it and press enter. And this, believe it or not, is actually the slope that you get from the plotting tool. The only downside to it is that it doesn't give you an uncertainty, and so you still need to use the plotting tool to get the uncertainty. But this is just like, for instance, you could do that, once you get this and you know that it's a reasonable value. I mean, that's pretty close to 9.8. You can, do this at home or whatever. It depends on if you're running late or something. I just wanted to show you guys. Okay, so now let's talk about the actual equipment. So we kind of have something similar to last lab, where we used the picket fence, and we converted the length of the segments and used that to convert to physical units. Basically, what this paragraph right here is telling us, that last lab we didn't have to do that. We could have clicked on data, we could have clicked on user parameters, and then we could have inputted the thing called the photo gate distance as that segment that we could have just measured. Basically, last lab was just trying to get you to do more math when it was unnecessary. And so what we're doing here, this value right here is almost exactly the same as the small d that we used last time. And why is that? So the whole circle is like the distance around the circle. This is supposed to have 10 spokes. All your wheels have 10 spokes. I just forgot. So yeah, this wheel has 10 spokes. And if you take a look at it, so the radius is some value, and the circumference is 2 pi r. So that's the distance around the perimeter of the circle. And what you can do is divide that by the number of spokes, which is 10. So then you get this value that is supposedly the spoke length. So if you read this thing, it's the distance per spoke. It's a little bit misleading because it's actually more like the exact same thing that we did from last lab, where the D was, it wasn't only the black segment, it was the black and the clear segment. Because if one thing you can do is kind of just test it for yourself. And so you can measure one of those spokes near the end of it, because you can see that the laser is kind of getting it towards the end. So if I measure one of those things, it's more like half a centimeter, not really 1.5 centimeters. However, if I measure the spoke and the gap, that is actually 1.5 centimeters, which is, if you convert meters to centimeters, it's moving the decimal place 2 things. And so it's like 1.5 centimeters. So that's just kind of some wording that they, it's really just like the segments from last week. So I just wanted to convince you that we could have done last week easier by not even, we could have just measured things with a ruler, and then we could have went to Logger Pro and input this parameter where in last week we would have, what was it, like 5 centimeters or something like that. Anyway, so some other, I guess, tips and tricks or technical things that you might mess up. If you can see here, what I have is on the Zoom screen share, I have the string on this little like bar that goes across the weight, which is the incorrect way to do it. You want it like this, where you see the string is like all the way across the spoke, because in this case the spoke moves and we measure that spoke. Because remember, like the discussion question about the photo gate, all the photo gate is doing is a stopwatch. It's just like blocked, 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 unblocked, unblocked, blocked, unblocked. So it's not like, without us putting in that parameter, it has no idea what a distance is. It's just time, 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 time. It's mostly just a glorified stopwatch for the laser on it. So unless we do this, the Logger Pro won't pick up any data. It still will, like the apparatus will work if you hang something on that little bar that holds the spoke. It's just not what we're going to need for data. And 2 other things I wanted to mention. Because you guys aren't the Monday class that I had yesterday, you might already have holes in your string. Yeah, so most people's strings like probably already have holes in them. If you don't, one way that I found that was kind of easy to tie knots, if you're not like a, I don't know, like a fisher person or whatever, is to use this pole and kind of tie a knot like that and make it super tight, like do a double knot, make it like permanent. And then you can slide this thing off the top by unscrewing, and then you can kind of just take your knot off the pole, and then you have a knot. Some other things. Over to Logger Pro. That screw tightens things, and this screw kind of angle stuff. You usually don't have to move it, but if it is tilted. Okay, and so then you kind of take your string and you put it through the green. Most of your things are green. The green holder, so that you can put that. And then it's it's at when it's not on the spoke, it'll rest on that bar that you're not supposed to put it on. But while you're setting everything up, you can do that. And then you grab some weight and you put it in the whole thing, the other whole thing. And then make sure that you're holding your heavier mass, because the heavier mass is what's going to determine if the thing is moving or not. So you hold this, you put it on the spoke, and then make sure my Logger Pro's on. It is on. And then one thing that I found, if I held the actual mass itself, I was actually getting kind of crappy data. I actually thought it was better if I held the string. So I want to put the heavy mass right below so that I'm getting the most amount of data. I'm going to head over to Logger Pro. And it does come off the spoke if you don't hold things right. So another thing you can do is put it on, and then hang or put both of the masses on the desk. Hold them. And then I'll tilt this over here so you can see what Logger Pro does. And so I'm going to get rid of all these linear fits because they're from previous runs. And then I'm going to set it up. Continuously get tangled in each other. There we go. Put heavy mass up at the top. I hold on to the string with my finger. Then I press collect and wait a second until it starts erasing continue. Now it says waiting for data, so I can drop it. And yeah, so another thing, this lab is quite violent in the sense that these knots aren't very secure. So what usually happens is this thing flings off and potentially breaks your computer. So keep your computers safe. Anyway, so now I have data. Oops, what did I do? It went away. Anyway, let me put a heavier mass on here so it's not so abrupt. The more mass difference you have, the more the faster it will go. So now I'm going to do like 20 gram mass difference instead of whatever I did before, which is probably like way too much. Okay, now I'm going to press collect, wait for data, stop, and now you can see this was when they hit. Like this is free fall. I drop it, it goes up, and then some crazy stuff happens. So all this you ignore. What you want is the straight line. I'm going to highlight only the straight line part. You see the squiggles kind of start here, so I'm just going to stop it. Even if I want it to be better, I can see squiggles here already. Hopefully that's on the, yeah, you can see it. So I'm going to only take this part. I'm going to just highlight the absolutely straight line. And then, as usual, analyze, linear fit. And as you can tell already, this graph that they have on display is velocity and time. So already, if I do analyze and linear fit, the slope is already my acceleration. And you can see it in the meters per second squared. And the way that it's getting a distance is because if I look at data and user parameters, it has like this is what we could have inputted last week for small d, and we would have, instead of segments per second, would have already said meters per second. So sorry. Yeah, and that's basically it. And then you just do this. So this would be, for instance, your that would be your acceleration 1, and then you drop it again, get acceleration 2, drop it again, get acceleration 3. This one was actually, usually I'm not super pedantic about, like you can see I barely did, I didn't even do the third one. But for this one, like when I only did one trial for all of them, my value was pretty bad. It was like 15 or 20 or something like that. But once I did a second and then, found the average and used the average instead of just, my usual lazy method, I actually did get a decent value. So that is all. I will allow you to start playing with stuff and ask questions. This one's already set up, so just leave it. Okay.